Thank you so much. Wow, if anyone had imposter syndrome, I've definitely got it now. Thank you so much for coming to listen to my lecture. And I know many of you have travelled very far, Manchester and Newcastle. It's great to see my mum down here from Newcastle. So thank you so much for coming. I'd like to talk to you about thinkering our way to solving the grand challenges. And I think this is really, really important. Have you ever been in a meeting where somebody does that all the time? Yeah. Or maybe you do it in a meeting. Yeah. It's really annoying. I'm annoying myself doing it now, actually. Have you ever wondered why people do it? I think it's because they're trying to intuitively help themselves to think more creatively. When we use our hands to tinker, we are engaging in that part of our brain that generates sensory images in our minds. And these images help us to develop a deeper understanding of reality and the world around us. From the moment we are born, we seem to have this innate ability to grasp objects. We use our hands to explore the world around us, around our surroundings. We use them for comfort and to connect and create the world around us. So perhaps it's no surprise then that our hands can be incredibly powerful tools for our mind, helping us to think more creatively and to ease anxiety. In the 19th century, doctors would prescribe knitting to women who suffered from anxiety. I'm not quite sure what they prescribed men, but women, they had knitting. In Michael Ondaatje's novel, The English Patient, the word thinkering was coined, linking the way we create and understand concepts in our mind with tinkering, using our hands. And this playful expression is used to describe when we use our hands to engage with something, whether that's putting together a toy, doing the washing up, or I want to show that thinkering is key for the next generation to solve the engineering grand challenges we all face. There are 14 world global engineering grand challenges of the 21st century. And these include things like engineering better medicines, reverse engineering the brain, providing access to clean water for everyone, and to engineer the tools of scientific discovery, which is the challenge that I work on. And I'd like to share some of those challenges with you this evening and why I think we need to tinker our way to solving these. So I engineer the tools to help better understand the universe, and I use radio waves to do this. So just to have a quick recap on radio waves and the electromagnetic spectrum, whether you're sitting at home, walking down the street, sitting here this evening, you are bathing in a sea of electromagnetic waves, undulating particles of no mass that zip-zap invisibly through space at the speed of light in a wave-like pattern. And so we have radio waves and microwaves here, which is the part that I work on. Now, these photons, these particles with no mass, called photons, these have different amounts of energy. So at the long wavelength end of the electromagnetic spectrum, they have quite low energy. And as you get higher, so microwaves would have a bit more than radio. And then as you get higher and higher into the high energy rays, cosmic rays. And like I say, I sort of work around the microwave and radio region. And I remember working out at Jodrell Bank Observatory. It's a radio astronomy facility. And my first job out there was as a microwave, RF and microwave engineer. And I remember saying to my friends, oh, you know, I've got this new job, I'm a RF and microwave engineer. And for years, they thought I built microwave ovens. I think they probably still do, to be honest. What I did, in fact, do was design instruments to receive the radio signals from space using telescopes like this one. For those of you who don't know what Jodrell Bank is, it's a radio astronomy facility out on the Cheshire Plains near Manchester. It's owned by the University of Manchester. And this is their biggest dish. This is the Lovell telescope, 76 meters in diameter. It's a beast. And so I worked on designing instrumentation for this. And so what happens is we have our signals that come in from space. So with a radio telescope like this one, what happens is the signals then hit the dish and then are collected right in that top of that tower. So all of the signals get collected right up here. And so we collect our signals, and then the very first thing that happens to them is they're amplified. And this is really, really important. So this amplifier, this very first amplifier here, has to be very low noise because you don't want to increase the noise that's coming in. You just want to have that lovely pure signal from space. You don't want to add any noise to it. You don't want to degrade that signal in any way. And so this low noise amplifier, or LNA, is very, very important. And then what happens in many receivers is you would then down-convert that signal. So you'd mix it and down-convert it to a lower frequency, and then you might amplify it again here. And the reason you do that is so you can digitize all the back end. So when you have all of the signals in the back end, you can manipulate them, you can reduce that data, and that's much easier in the digital domain. So these astronomical signals are very weak. And like I say, you have to amplify that signal, but not the noise. And so this LNA, this low noise amplifier, is the most crucial component, I think, in a radio astronomy receiver. And the reason I'm bigging these up is because that's what my research team work on. We design low noise amplifiers, or LNAs. And so right at the heart of that radio astronomy receiver, you would have a cryostat, which is just sort of like a very efficient fridge. And so we cool the low noise amplifiers down to about 15 to 20 Kelvin, which is around minus 250 degrees Celsius. And so inside this cryostat, inside this fridge, you would then have a low noise amplifier. So this thing can be about this big-ish, and it's usually gold-plated brass or gold-plated aluminium. And then right in the center of that tiny little thing, right in the center there, is the integrated circuit. That's the LNA, the important part. And so these integrated circuits are called MMICs, monolithic microwave integrated circuits, or MMICs. Now, you have integrated circuits or MMICs a lot in our cell phones and our mobile phones. You have these a lot. These ones are very, very special because they have to be virtually noiseless. You know, we don't want to add any noise to that lovely astronomical signal that we're trying to receive. So they have to be virtually noiseless, and we have to cryogenically cool them. So they have to be able to work under such operating temperatures. And so we do lots of different designs using lots of different semiconductor materials. And they're different in size. So this one that you see here is the integrated circuit. That's 2.5 millimeters by 2 millimeters. We actually do smaller ones. I just want to show you how small they are. I don't know if you'll be able to see this. Right in the center, there is a millimeter. I think it's about 1.5 millimeter by 1 millimeter in the center there. That is what we do. So small is beautiful when it comes to this. These are our LNAs, very, very crucial for all radio astronomy receivers. So we work on LNAs for both Earth-based and space-based radio telescopes. Now, we've been broadcasting radio signals as humans into space and listening to radio signals from deep space for well over a century now. And that's allowed us to realize how much there is beyond what we think we know. And so in the past few decades, larger and more powerful telescopes have been built to look deeper and deeper into space. And my team are very fortunate to work on two groundbreaking projects. And I'd like to talk about the two with you now. The first is called the Atacama Large Millimeter Submillimeter Array, or ALMA. And it is a revolutionary instrument in its scientific concept and its engineering design. So these are the dishes that you can see here. There are 66 of them, and they are on a plateau in Chile. So they're about 5,000 meters above sea level in Chile. And they're high-precision antennas. All of these antennas will work together at millimeter and submillimeter wavelengths. Now, it's so sensitive, it will open an entirely new window on the whole of the universe, and that will allow scientists to unravel long-standing and important astronomical mysteries. And so the part that we work on is this red dot here, which is the detector, the front end here, the electronic detector. And that amplifies the signal and then converts all of the signals from analog into digital of all of the different dishes here. And again, this cryostat, this big fridge, is where you'd house the low noise amplifiers in here at around minus 250 degrees C. And this is already operational now. So I want to show you a video sequence of the ALMA antennas and what they are observing here. This video sequence that you see here will start with a broad band view of the southern sky, and it will slowly zoom in on a constellation. It's quite a faint constellation called the Clock. Now, when we get closer, we'll see a striking spiral galaxy known as NGC 1433. And the central part of this galaxy hosts a supermassive black hole. And observations of the surrounding areas of this supermassive black hole using ALMA and only ALMA have revealed both a spiral structure to the molecular gas, as well as newly discovered outflow of material. It is truly revolutionary, this machine. And to tinker, to thinker, and be allowed to tinker and thinker on a machine like this makes you feel very, very proud to do this in your job. So engineering the tools for this sort of scientific discovery is certainly challenging, very rewarding, but certainly challenging. The surface of the radio frequency dishes themselves will not deviate from an exact parabola by more than 20 microns, 20 millionths of a meter, each one of them. And this prevents any of the incoming radio waves from being lost, so that these resulting pictures that you get with ALMA captures as much of that distant cosmic light as possible. And there are so many more amazing challenges for ALMA, which make it such an interesting project to work on. The supercomputer that's needed is the supercomputer that operates at the highest altitude in the world. The images have 10 times more detail in them than the Hubble Space Telescope images. 17 trillion operations every second will be needed for this. It's the fastest computer on an astronomical site ever, and it's equivalent to billions and billions of pounds worth of personal computers to make all of the necessary calculations on here. The correlator that you see here is the piece of equipment that will bring all of these different antenna signals together, and so you build up one big picture of each of the dishes themselves. So this correlates the signals in here. This correlator here has 20 million welding points on that correlator. And all of this must work exactly the same, no matter what the temperature. And that's pretty tricky to do when the maximum temperature between day and night could be as much as 40 degrees Celsius. It's really, really tricky stuff, this. Now, the ALMA frequency bands are, so you have quite a lot of these cryostats in ALMA, and they work from 35 gigahertz up to 950 gigahertz, so just under a terahertz. So if you think your mobile phones are working at a few gigahertz, we're starting here at about 35 gigahertz up to just under a terahertz. If you want to think of that in wavelengths, that's about 8.6 millimeters to 0.3 millimeters in wavelengths. So the low noise amplifiers that we are producing are pushing the very limits of semiconductor technology. It's not the type of place that, or frequency place that you tend to see this semiconductor technology. So we're really sort of trying to push this technology to its very, very limits, and we're reaping the rewards for it right now. So I just want to show you an artist's impression of a lovely star. It's Orion Source I. And if anyone has any questions about this, Gary Fuller, the astrophysicist who I work with a lot, sitting in the second row here, can answer any questions you like on this. It's a collaborator of ours who's given us this picture. So it's a young, massive star, about 1,500 light years away, and new ALMA observations have detected, I love this, have detected a ring of salt around this star, sodium chloride, table salt, around this star, surrounding this star. And this was the first detection of any kind of salt associated with a young star. So they've taken ALMA, this revolutionary instrument that we have tinkered with and created, and they've started to observe this. They weren't looking for salt, but what they found is that salt was glowing at millimeter wavelengths here. And this is what revolutionary instruments such as ALMA, I think, can give you. You find the unexpected with them. So what does this mean? That salt is radiating, glowing at millimeter wavelengths? I don't know. We don't know yet. I don't think anybody knows, do they, Gary? No? Good. So, they weren't expecting to find it, but what it means is they're finding things out that the next generation will use to discover even more. And so you have this telescope, ALMA, which is just finding the unexpected, the unknown. And I think that's what links the two projects that me and my team work on, because it is looking for the unknown. So it brings me to my second project. And we work on this with hundreds of engineers and scientists around the world to build the largest science facility ever built by mankind and to probe deep into the universe. What will they discover? The unknown. It's called the Square Kilometre Array, or the SKA. Now, the SKA will be made up of hundreds of thousands of different types of antennas, and you can see an artist's impression here about what it might look like. And they'll be covered across a huge area in Western Australia and in a remote area in South Africa. Now, it's currently being built, but when complete, the sheer size of the SKA will make it 50 times more sensitive than any other radio instrument ever. And that will enable us to answer key and ambitious questions in cosmology, astrophysics, and fundamental physics. I think this is the best, my favorite fact of the SKA. It will be so sensitive, it will be able to detect an airport radar-like signal on a planet 10 light years away. 10 light years away. This is one experiment. Now, there's several spectacular parameters, I think, to the SKA. Again, this is another artist's impression of what the slightly higher frequency, the dishes, might look like in this. It's estimated that the low-frequency dishes alone will generate more than 5 times the global internet traffic. More than 5 times the global internet traffic. These low-frequency things here. So in phase 1, there's going to be 130,000 of them and around 200 dishes here, and that is just phase 1. By the late 2020s, it's hoped to have millions of these things spread across Western Australia and South Africa, and thousands of these dishes. So the amount of data this thing is generating is enormous. Just enormous. If we could express, when it's all built, if we could express the SKA data collected in one day and download it as a song and play that song, the song would take 2 million years to play back. That's one day's worth of data. The high-performance central computing engines needed here will need to perform 10 to the 15 operations every single second. Transfers of 1 terabyte images will need to be taken and spread across the world every single minute. If this was built now, the whole of the SKA, so we're just doing phase 1 at the minute, but if the whole thing was built now, we'd have to throw away up to 90% of the data because we just can't store it. So that raw data, you'd have to throw away up to 90% of it. It's tragic, absolutely tragic, because I think you'd miss those sort of serendipitous science moments where you think you're observing something over here, and this data over here that you weren't really bothered about, you start looking at it and you find your wow moment over here. What is it over here? If this was built now, we wouldn't be able to do that. We'd have to throw all this away and just take what you wanted to observe in the first place. I think it's tragic. So we need the next generation innovating, tinkering with their hands, coming up with creative solutions to solve this grand challenge and all of the other grand challenges that we're facing. And how do we tinker? I think we tinker by getting out of our comfort zones. that's where the magic happens. And it really doesn't mean you have to achieve all of the time. You have to fail if you're over here. And let's celebrate those failures. They are fantastic. And they make you a better scientist and a better engineer for failing. But that's where you need to be, way out of your comfort zone. And so it brings me to my sort of thinkering project that I worked on, and it certainly continues to take me out of my comfort zone. I'm already out of my comfort zone because one of these robots doesn't work tonight. But it brings me to the Manchester Recycled Robot Orchestra. I just want to give you a bit of background as to how myself and a wonderful lady called Arinma, who's hopefully in the audience somewhere, there she is, came up with it. So have you ever been in that situation where you are completely deprived of sleep? And it's like you've taken some mind-bending drug because you're so tired. And you think of this great idea, and in this sort of mind-altered state, you think it's like the best idea you've ever had. And then you talk to others, and they're like, oh yeah, that's a really good idea. And so this, finally, you talk to more people, and then, yeah, let's arrange a meeting about this. And finally, you do get more sleep, and you go to the meeting, and you're in this meeting, and they're all talking about this crazy idea, and you sort of look to someone and you go, who thought of that? And everyone's like, oh, it was you. Oh, right, okay. That's what happened to me in 2015. I was on maternity leave with a three-month-old. So if anyone's been in that place, you know I was massively deprived of sleep. But I'd been asked to attend a meeting to discuss what we could do as part of Manchester becoming the first UK city of science. So I wanted to do two things with this. I wanted to try and get engineering on the map a little bit more, the engineering and sort of technology side, and the sort of hands-on science, so this whole idea of tinkering, of thinkering, and to get the public involved a bit more, and to have science in the city itself. And in the same meeting was wonderful lady Arinma, who is a lecturer in science communication, and the most wonderful lady in citizen science as well. And so we talked about a citizen engineering project. And we were like, oh, has there ever been a citizen engineering project? And oh, I don't think there is. So we'll try it. And so we tried it, and we thought, okay, what would capture the imagination of people in the city of Manchester? And so we thought, okay, we need to try and capture the imagination of people who really like science and technology to begin with. So like a good student, I Googled what young people's imagination in science and technology, what they would like, and I got space and the universe, pyramids and ancient civilizations, dinosaurs, and robots. And so I thought, we'll go with robots. So Arinma and I thought, okay, what would bring the creativity of people together to try and show how creative scientists, technologists, engineers are, and how they think so much, and why it's so important that they do. But we also wanted to bring the creativity of other people as well, who perhaps didn't see themselves as scientists or engineers, so maybe people who related more with music or the arts. And so we decided on a robot orchestra. But we didn't want to do just any other robot orchestra. There are lots of amazing robot orchestras out there. I was very fortunate to be part of the Christmas lectures, and I saw Joe Myers-Co before, who was the producer of the Christmas lectures. He worked tirelessly to get all of these robots together for the robot orchestra. It was an amazing project. But we wanted to have, fundamentally, we wanted the creativity of people and the thinkering of people to sort of all come together and to take people out of their comfort zones. So we thought, okay, what would take people out of their comfort zones? Okay, what do we need to do a robot orchestra? Well, we definitely need engineers. Okay, so are there any engineers, technologists in the room? Some? You guys should be putting your hands up, my research team here. Okay, how about this? So engineers and scientists, engineers and technologists in the room, okay, I'd like you to design something, but I'm not going to give you a specification. I'm not going to give you how many subsystems there are, but they're going to be lots and lots of subsystems, and I want you to make sure you can all put them together, and it's got to be done on a very specific date. By that date, that can't change. Oh, and by the way, can you make that whole system from recycled or upcycled materials? Are the engineers feeling a bit uncomfortable? I was feeling massively way out of my comfort zone with this. But lots of professional engineers took up the challenge to help us, including Siemens, and they embraced the project with huge amounts of enthusiasm and well-deserved skepticism. I love this quote from Adam, who was one of the graduate engineers we worked with at Siemens. The journey from concept robot orchestra to actual robot orchestra has been wild. That's the clean version of it. But it was so great. You know, they really did embrace it as we wanted them to embrace it. Okay, so what about musicians? Have we got any musicians in the audience? Yeah, some. Okay, how about this? We want to try and take you out of your comfort zone. We'd like you to compose a piece of music, but you don't know what any of the instruments are. You don't know how many you're going to get. You don't know what they're capable of when you do get them. You've got absolutely no control of the timing. But can you just do it and by this date, and that date is non-negotiable? Is that okay? Thankfully, Manchester's Halle Orchestra stepped up to this challenge, and Steve Pickett, who's the education director for the Halle, was instrumental. That's a really bad pun. I wasn't meant to say that. Was very, very important in the Robot Orchestra project. And so the final piece of the puzzle was the public. What would take them out of their comfort zones? How about you design something, but there's no one right answer? You're basically given a blank sheet of paper and said, design a robot instrument. You can work on an engineering and technology project. You can use recycled technology or upcycled components to build any instruments you want. So I'm trying to get people out of their comfort zones. What I hadn't appreciated at the time was children have no concept of a comfort zone. I honestly don't know whether they're always in it or they're always out of it. I'm not quite sure which one it is, but they have no concept of a comfort zone. It was brilliant. It was absolutely brilliant. And so the Manchester Robot Orchestra was born. The Robot Orchestra is a citizen engineering project, so it's designed to try and bring together the ingenuity, the creativity of the public.
The recycled orchestra has never been done before, using the various robots to try and get an orchestral piece. The main challenge has just been trying to make sure that we can find a common interface with them.
It's a real hub of excitement at the moment.
The variety of instruments that are here is absolutely incredible.
The challenge I'm finding today is just working with the different sounds that these instruments make and trying to create a piece of music that will sit together.
There might be a few tweaks that need to be done, get them all wired up and hopefully get a song playing today.
I think the impact of it is the really important thing. That's the plan. So come on, let's do it!
So we had hack days, rehearsal days to prepare for this first live performance of the Robot Orchestra, which was going to be at the opening ceremony of the European City of Science in Manchester. We had over 300 school children, hackers, makers, teachers, musicians, tinkerers of all ages involved in this project. It was brilliant. And we basically gave them a bag of bits. And in that bag was an electronic brain, which was a very, very scaled back version of something like a Raspberry Pi. It's called a crumble. And so for primary school children, they are starting to code in something called Scratch. And so this very small, very simple electronic brain was able to work with the programming Scratch, the program Scratch. And so we gave them this electronic brain and a few sort of wires and bits and bobs to go with it, a few little motors and servos and things to go with it. And we made some videos to help them along. But we definitely didn't want to show them, this is how you build an instrument. And so we got so many different things because we didn't tell them. what we wanted. And that was the brilliant thing, I think, about it. It just seemed to capture the imagination of so many more people than I think both Arinma and I ever imagined it would. We had so many different, like a variety of industries and societies that wanted to be involved, from the Women's Institute, the Manchester Transport Network, the National Trust, who donated some cotton looms, which I have here this evening. And of course, we needed a conductor to bring it all together, an electronic conductor, and that's what some of the guys at Siemens worked on as well. So they produced their electronic conductor. They called it graphene because it was a good conductor. Sorry for the joke. And so they brought all of these instruments together to get them to play, as actual, as an orchestra rather than just individual instruments. But it was the children's imagination, or I just could never find that sort of boundary of where children's imagination would end. And it was their sort of tinkering and thinkering that really got my attention. So I wanted to share a few of the videos with you here. These are all from primary school children. I love this. So you have an empty food tin here, and you have a plastic cup here with some rice in as well. And this was called Beats by Bowker. Bowker Vale were the primary school. And that was brilliant. It was actually the cardboard that didn't travel very well. That's how I couldn't show it to you tonight. The cardboard itself is not traveled very well, so we need to make a wooden version of it, I think. Here's another one.
This is our Robo Drummer, made entirely of upcycled computer parts. We've programmed him using the Crumble software, and his arms will go up and down via these servos. They'll hit the heat sinks, one at a time, and one will hit it at a greater speed than the other. We hope you enjoy.
I loved Robo Drummer. It's so brilliant. And it does make a really good percussion addition.
1, 2, 3, 4.
This one's called Breakfast Bot. And what these are all different types of breakfast bowls, including sort of dog bowls and things here as well. And so what they did was they got bowls and spoons and used the motor and their little electronic brain, their Crumble, to hit the bowls. Not only did they do that, these primary school children tuned this. This was actually in tune. And so they calculated the size of the bowl, etc., that they'd needed to get an A or a B flat or an F sharp. And so this was all tuned as well. I think the thing I love about this video as well is the children are all hiding behind these as well. They loved it. But this is just a flavour, and I just have a flavour this evening to show you. But we had instruments from everywhere. The Siemens engineers took a big industrial drive that you'd get in industry. And if anyone ever wants a big industrial drive to play God Save the Queen, Siemens are your people to do that for you. We had robots from Lego. We had robots from Pringle crisp cans with chopsticks that would hit a tin of beans in front of it. And so they would drum. We had hexapods that would use the nuclear research that we made play a piano. We just had anything and everything you can think of. And the reason was, it wasn't us that were thinking of it. It was mainly children and thinkers of all ages were thinking of these instruments as well. So these all played with a 9-piece 9 musicians from the Halle Orchestra. And the result was just amazing. Irina and I were so proud, weren't we, on that day. We had this opening ceremony, so you have very, very important people from the whole scientific community around the world heading to Manchester, and we were playing at the opening ceremony. And we did the robots proud, I think, hopefully. But yeah, the whole thing was just amazing. So I just want to show you some here tonight. So hopefully I'm going to go to Cheltenham Science Festival and do a much bigger version of this. And so we're just trying to work out what tune to play with them. But I just wanted to give you a flavour of what's happening. So I'm going to go to the one that's not working first. It hasn't travelled very well, unfortunately. But this one is Plant Pot Bot. And so what you have is Plant Pot. There is a little electronic brain behind here, you can see here, and it is controlling these 2 wheels that have the spoons. And so what it does when it's plugged into the conductor and working, just plays, so you get the percussion from here as well. Okay, percussion is the things that I've brought because they seem to travel a bit better than other things. I'm just going to switch them on. So what we have here, again, this connects into the conductor, but then we can just have a little box to press the button just to show you guys tonight. This is the crumble down here. You can see it down here. This is the little electronic brain, so we have 2 of them on here. And so this is just, we're able to just hit it here, but then when this is all connected, obviously you can play lots of different things. And so we had, this was donated, as well as all of the little bits from everywhere were donated into the schools as well. This is, these are the looms that I said from the National Trust. So these are the looms from the old cotton mills in Manchester in the Industrial Revolution. And so we have them here. And then we actually use this as a sort of a metronome as well, but it can be part of the percussion as well. This is our light that flashes in time. That was donated from the Manchester Transport Network, so this is off a tram. They also donated us an original whistle. If anyone knows any of the trams in Manchester, they have this very sort of very unique whistle sound. And rather disappointingly, it's on an MP3 sound now, so they don't actually use these old horns, so they donated one of them to us as well. So we have this flashing, and then the horn also plays. And then massively in the spirit of recycled or upcycled materials, I'm definitely in an audience where you are going to remember what these are. That's not always the case. Floppies. Remember these things? Yeah, we never needed more than 1 floppy. That's what Bill Gates told us years ago, 1.44 megabytes. That's all we needed to store our data. Wouldn't work for the SKA now. So these are all floppies and old floppy drives. And so we've just taken the sort of tops off them here. And so what you'll hear when I play some music is the motors working. And of course, this is all due to Michael Faraday, so it's quite nice that it's sort of Michael Faraday lecture. But it's the motors in the floppy drives are the things that you'll hear. And so what we're able to do, this has got a bit more of a fancy electronic brain in here, and it brings in MIDI files, so music files, so that these floppies can play a range of notes. So we can sort of feed in a range of notes, and then we can tell it what to play. So I'm going to play some tunes, see if you can guess what they are. Can you guess what it is? Okay, right. I'll get it to play another one. What about this one? If anyone likes 80s rock, you should get this one if you like 80s rock. That was our very own version of Eye of the Tiger. Right, I just want to play this one. This is Hall of the Mountain King, and this is a piece of music that we tend to get the whole Robot Orchestra to play, and so we sort of build up. We do it sort of quite gentle, and then we build it up further and further, so it gets faster and faster. And I remember one of the times that we were doing an evening show one time with the whole Robot Orchestra. There was a whole bunch of school children there, and I said, okay, now the Robot Orchestra is going to play, at the end, it's going to play this tune. Can anyone guess what this tune is? And we played Hall of the Mountain King. And loads of hands went up, and there was this little girl in the front, she was like, me. And so I was like, yes, what it is? And she went, the theme tune to Alton Towers. Well, yes. But this is what she heard. So this thing can play lots and lots of different tunes, and it has that lovely sort of low bassy sound that it ends up working quite well in a robot orchestra as well. So we had all of these instruments, and then, like I say, it just seemed to take off. You know, we had, it almost sort of went viral, really. We had millions of hits on social media from that opening ceremony performance. We had Sputnik News in Russia picked it up. So we were on Sputnik News. Al Jazeera TV picked it up. And so we were played in airports all over the Middle East. The Robot Orchestra was being played in airports all over the Middle East. And then we were asked to take it to Maida Vale Studios here in London to be part of a documentary on iPlayer for Can a Robot Replace Ed Sheeran? Which was, of course, we all know it can't. It's a documentary on iPlayer, but it was also played on Radio 1. So I just want to give you a little taste of it here. And all of the instruments, every single one of them, apart from the humanoid robot that you'll see is Ed Sheeran, is part of the Manchester Recycled Robot Orchestra. Can you imagine how these children felt who created all of these wonderful instruments? Their instruments were backing robots for a robot Ed Sheeran and played on Radio 1. They were like the coolest children in school all of a sudden. But what they were also doing was they were starting to think about what they'd learned as well and the habits of mind that they developed as part of it. They'd used their hands to help visualize things. They'd built up resilience. They'd certainly failed along the way, and they enjoyed that failure, and they learned from it as well. They were problem finding and creative problem solving. We will solve the grand challenges that we face in the 21st century by doing what's in the middle of this diagram. Make things work, or make things work better. And that's what we need to be able to do. And that's what a thinkerer does. So for me, the Robot Orchestra has a serious side as well. It shows collaboration, that scientists, engineers, musicians, artists can speak the same language. It hopefully shows policymakers and MPs that making children choose between arts and sciences before they're 16 is a very wrong thing to do. It shows that my research will have most impact when I take it out to the community, and most importantly, it shows what children can do when they are allowed to play, to tinker, to help their brains think more creatively, and to fail along the way. But perhaps most importantly, it's just fun to work on. It's a lot of fun to work on, to show that 5-year-old or remind that 75-year-old how much fun science, technology, engineering actually is, and how you're just steps away from solving the engineering grand challenges by applying those same habits of mind. Because it's that fun element that will help us to inspire the next generation so that they do solve these global grand challenges. I asked a friend of mine a few years ago now, actually daughter of a friend of mine, why, I was always saying, I think it's really important that I get out of my comfort zone, I get out of the university, and I go and talk about my research and hopefully try and help inspire the next generation. And I think that's really important. And she was like, yeah, I think it's really important. I was like, do you? Why do you think it's important that we do that? Here's what she said.
I'm you in the future. So if you help me now, in the future, I can be better than you.
I'm you in the future, so if you help me now, in the future I can be better than you. What a great motivator for every single person in this room. And I think it's especially important for the engineers and the scientists in the room, because not a lot of people know what we do. An RF and microwave engineer working at Jodrell Bank does not make microwave ovens. Society, including children, has an understanding of what many professions to do, such as medicine, because we've all had first-hand experience of it. So it's ironic that technical innovation and hands-on engineering, that result of thinkering, is everywhere, but it's invisible because it's woven into the very fabric of everyday life. Many people simply do not know what we do, but why should they? If we aren't out there showing them how ingenious these people are and why it's so important to tinker, to play, to help your brain think more creatively. So if our eyes are the window to our soul, I'm a firm believer that our tinkering hands are our passports to creativity, to thinkering, and to solving the grand challenges. Thank you very much for listening.